So at this point, it should be becoming very clear to us that a classification tree takes the training data, which is historical data, and based on a bunch of rules that it arrives at through the process of machine learning, it breaks up the initial data into a bunch of buckets and then makes decisions based on the composition of each bucket. Ideally, we want the buckets to be of reasonable size, at least 20-30 cases in each bucket, and we want the buckets to be as homogeneous as we can make them to be. By homogeneous, we mean that the buckets are highly skewed in terms of the target attribute composition, right? For example, mostly accept or mostly reject. We don't want a more or less equal distribution of accept and reject because then making a decision based on that even distribution may not, it doesn't seem like a good idea. Okay, so with this intuition, let's continue and look at the process some more. Okay, so let's understand these key intuitions. So obviously, let's consider an example, right? So we are making a conclusion based on the composition of each bucket. By composition, I mean I've got a bucket and this bucket has, let's say, 50 cases, and let's say 40 of them are accept in the historical data and 10 of them were reject in the historical data. Then we can say, well, that looks like there's an 80% chance that if somebody meets the criteria to be in this bucket, then we should classify them as accept, okay, with an 80% chance, and reject with a 20% chance. Okay, so let's say that we are conducting a survey in two different towns. Okay, so survey one or two surveys. Okay, so we did a survey one in town X, and the average household income turned out to be 35,000. Okay, we are trying to find out what the average income in that town is. Okay, and we did a second survey, and the average household income turned out to be 38,000. Okay, same town, two different surveys gave us two different results. Okay, now obviously, which one do we prefer? Do we prefer 35,000 or 38,000? Okay, let's say that this 35,000 value was based on 40 people, meaning survey 1 talked to 40 people and their average income was 35,000. Survey 2 talked to 100 people and the average income was 38,000. So obviously we would say, I really would trust survey 2 more than survey 1 because it was based on a significantly larger number of people. Okay, so it could still turn out that survey 1 was the one which was closest to the actual average, but we would feel that it's much more likely that survey 2 is really a better representation than survey 1. Why? Because it's based on a larger sample. Okay, another way of looking at it is, well, suppose we repeated the survey. Okay, the same survey we repeated in survey 1 and we repeated in survey 2. Well, which area, survey 1, area 1 or area 2 is going to, has a higher chance of yielding a different result, right? Once again, we'll say since this was based on 100 people, it is more likely that the result I will get if I repeat it will be closer to 38,000 than if I did the same thing here with 40 people. It's likely to differ from 35,000 a lot more. Okay, so in other words, what we are saying is if I base my decision on a larger sample size, I am safer. My decision is more likely to be correct. Okay, I'm only saying more likely to be correct. There's no certainty, but statistically there's a smaller chance that we would get something off. Okay, that's really the basis of statistics. Okay, so other things being equal, prefer the larger sample size. Okay, let's look at another point. So let's say we did a different kind of study and we did studies in two areas, area 1 and area 2. Okay, so in area 1, we looked at 90 people, okay, and 50 of them were buyers, 40 of them were non-buyers. Okay, so the conclusion clearly is area 1 has more buyers than non-buyers. Okay, of course, this is only based on a sample. We are looking at only 90 people. There may be 20,000 people in that area. The only way we'll really find out whether it has more buyers or non-buyers is to talk to all the 20,000 people. We cannot do that. Okay, so we are making a conclusion based on a small sample. Okay, area 2, it turned out we looked at 100 people and 80 of them turned out to be buyers. Okay, so which of the two surveys would we have more confidence in? Okay, obviously we would be more confident of the second survey because the number of people surveyed was almost the same in both the surveys. This was 90, this was 100. But the majority here, it's like 80 to 20. Okay? Whereas here, it's only a slim majority of 40 to 50. Okay? So in that sense, this area 2 is much more homogeneous in terms of being highly skewed towards buyers, whereas area 1 is kind of mixed, almost equal buyers and non-buyers. Okay, so we would feel very confident in saying area 2 really, I expect, has more buyers than non-buyers. We can make the same statement about area 1, but we can't be as confident as we are in area 2. Okay, so again, other things being equal, prefer greater homogeneity. Okay, so what we're saying is two factors are important. One is, what is your sample size? And second is, what is the level of homogeneity that you're looking at? Okay, so again, look at the connection of what we are looking at here to classification trees. In trees, we are trying to break up the original training data into a bunch of buckets. Okay, and we are making a decision based on each bucket. Each bucket has a sample size and each bucket has a level of homogeneity. Okay, so what we ideally want is buckets which are as homogeneous as we can make them to be and yet do not have a very small sample size. We want them to have at least a reasonable sample size and a high homogeneity. Okay, now the reason we are talking about this is that the process by which the machine learning constructs the tree operates on this idea. This is what it's aiming to get. Okay, so let's look at this here. Again, let's say we got a tree. Don't look at the details. We just ended up with 2 leaf nodes. Okay, so here we ended up with just 3 cases in this leaf node, of which 2 were buyers, 1 was non-buyer. Right? So you may say, well, this is predominantly buyer because it's 2/3. The number of buyers is almost twice the number of non-buyers. So I am pretty confident in saying that somebody who satisfies these criteria will be a non-buyer. Okay, sorry, a buyer. It shouldn't be non-buyer, it should be buyer because buyers predominate here. Okay, so probability of buyer is 2/3. But then it's based on just 3 cases. How confident can we be? Because 3 is such a small number to base your decision on. Okay, whereas here you've got 9 non-buyers, 1 buyer, and therefore the probability of buyer is only 1/10. Okay, this should be non-buyer, not buyer. I've reversed the labels on both of these, I apologize. Okay, but this is much more predominant. The sample size is 10. That's one good thing. It's more than the sample size of 3 here. And it's much more homogeneous. It's far more skewed towards non-buyers than buyers. So we are very confident in saying that if a person meets these criteria, they will probably be a non-buyer. Okay, so that's how these rules are working. Okay, so more cases and solid majority or homogeneity. Okay, so let's say that we've got a tree which comes out like this. Okay, and this is the set of leaf nodes. Okay, so here you see accept predominates heavily over reject, 250 to 50. So the sample size is 300 and it's highly homogeneous. Okay, here accept kind of predominates over reject, 170 to 100, and here reject predominates, and here they are almost equal but small sample. Here also they are almost equal, small sample, and here it's kind of marginal. Okay, so we are good. These three nodes are all very good, but these three nodes are kind of iffy. Okay, so instead of just saying somebody will buy or not buy, we can say that if somebody arrives at this, falls into this bucket, we can say that the probability of them being given a loan should be 250 over 300, okay, which is 5 over 6, right? So we make the probability, instead of just saying this case is in majority, so decide based on majority, we can just say the probability is so much. So for each of the nodes, we can lay down the probability based on the proportions of the two cases here, accept and reject. Okay, so here is just an example of, let's say you got some data and you built two different decision trees, classification trees, okay, and the leaf nodes turned out to be like this. Okay, so which tree do we prefer? Which is the better tree? Okay, so we're going to look at the composition of the leaf nodes and see if the sample size and the homogeneity. Okay, so here it's 250 over 300, 170 over 270, 30 over 230. Okay, so here also it's predominant, right? Because 30, 230, 25, 45, 2 by 5, 200 by 350. Okay, so here it's 400 by 475, not very homogeneous. 87 by 105, they're almost equal. 30 by 130, yeah, that's quite a majority. 130 by 180, so 30 by 130, okay, predominant, right? But we would say that this is much better because this has, in the large size nodes, like this has 300 cases predominant, 270 cases fairly predominant. Okay, again 350 cases fairly predominant, 200, 150, no, more or less equal. Okay, whereas here it's extremely heterogeneous, big mix, except for this node, every other node, this node and this node, there's a big mix in the other cases. Okay, so which one is better? It depends on which has high sample size and what is the homogeneity. Okay, now of course it's, again, having said what I said, it's difficult to make a decision just by looking at this and say which is better, right? So we need a more objective criterion to compare which tree is better. Okay, so here let's say that we've got a tree, and this is the process. It's just explaining the process, right? So you take the root node, partition into two sets, take the remaining nodes, partition, 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 and until you hit the stopping rule. Our stopping rule, of course, is based on either min split or min bucket. Okay, so what we can see is that a classification tree divides up all the cases into discrete sets. Okay, so in this case, 1200 cases that came in were broken up into 6 different sets, right? One set has 300 cases, another set had 270 cases, another set has 230 cases, and so on. Okay, so what really a tree does is it takes all the cases in the training partition and breaks them up into a number of buckets. And all the cases in a particular bucket, they satisfy the same set of rules, right? Because the cases end up in a bucket based on the decisions we make. So ultimately, within a bucket, all the cases satisfied the exact same number of decisions. Okay, now we look at each bucket. We would like each bucket to be highly homogeneous, Okay. Uh, and we want each bucket to have ideally a decent number of cases, a good sample size. Okay. Now let's take same scenario. Now what we are trying to do is to say, well, how do I choose between two possible splits? Okay, so here we've got 600 cases coming into the tree, out of which, these are, let's say, income tax returns, and the return can either be normal or it can be fraudulent. Okay, now here it turns out that in our original data, 500 cases are normal, 100 cases are fraudulent. In other words, the number of fraudulent cases is about 1/5 of the number of normal cases. Okay, and then we do some particular split and it ends up like this. Okay, so out of the 600 cases, 300 end up here, 300 end up here, and here it's normal 250, fraudulent 50, normal 250, fraudulent 50. Okay, so each of the leaf nodes has the exact same composition as the original data set. Okay, so the split that we did here did not make it any easier for us to make a decision. Okay, the amount of uncertainty, the ratio is not. Ideally, what we would want is a greater homogeneity. Okay, so here the homogeneity is like 500 to 100, 1 to 5. And here also it's 1 to 5, here also it's 1 to 5. So this split did not increase the homogeneity of the node. Whereas take this split, same input, but this created two nodes in which normal was 490, fraudulent was only 3. Okay, and here normal is 10, fraudulent is 97. Okay, so the 500 normals have split like this. Okay, so you can see that each of these two nodes is more heterogeneous than these two nodes, much more heterogeneous. Okay, so fraudulent to normal is 1 to 5. Okay, whereas here, if you reach this side, you can say, well, extremely high likelihood of being normal. And if you reach here, you can say very good likelihood of being fraudulent. Whereas here you can't say that. The likelihood is exactly, in both the cases, we're going to say it's extremely likely to be normal. Okay, this didn't do a good job of separating the fraudulent cases from the normal cases. This did a better job. Okay, so this achieved more heterogeneity, homogeneity than the first one. So that's a better split.